Hi, this is Professor Kleitz. In section 16-5, I'm going to talk about memory expansion and address decoding applications. When more than one memory IC is used in a circuit, a decoding technique called address decoding must be used to identify which IC is to be read or written to. Most 8-bit microprocessors and microcontrollers use 16 separate address lines to identify unique addresses within the computer system. Some of these 16 lines will be used to identify the chip to be accessed, whereas the others pinpoint the exact memory location. For instance, the 2732 is a 4K by 8 EEPROM that requires 12 of these address lines, that would be A0 through A11, just to locate specific contents within its memory. This leaves the other 4 address lines, A12 through A15, free for address decoding. So A12 to A15 can be used to identify which IC within the system is to be accessed. So let's look at a circuit diagram that employs this technique. So in this figure, the 2732, like I said, is a 4K by 8. So to get 4K different locations inside this chip, you need A0 through A11. That's 12 address lines. 2 to the 12th is 4K. So all of these 2732s, and in this diagram we're actually going to have 1, 2, 3, 4 unique EEPROMs, 4 of these 2732s hooked up to the A0 through A11 address lines. Now the unused address lines, which are going to be A15, 14, 13, and 12, are coming down from the data bus. And so we're tapping into the 16-bit address bus for the high order hex digit, which is A15 through A12, and then the A0 through A11 12 address lines come down into each individual EEPROM. Now to determine which EEPROM is actually going to get selected, we have these chip enables which are coming from a 1 of 8 address decoder, the 74LS138. So we're going to use these A15 through A12 address lines to make this address decoder select either this output, this one, or this one. And these lines are going to go high, low, high in accordance to the microprocessor's low read pulse. So when the micro issues that low read pulse, that enables this chip to work because the EN3 is tied high and the EN2 is going to be made low, and we'll look at that scheme in just a minute. So all the enables are going to be satisfied in accordance with this pulse. That pulse will come right through on whichever line got selected by the 8, 12, 13, 14 lines. So for example, if you put 0, 0, 0 on these lines and the microprocessor issued a low pulse, the number 0 would be activated, the not 0 would be activated, and that goes right to the chip enable of the first EEPROM. So the remainder A0 through 11 bit address bits lines are going to be used to address exactly which location within this EEPROM you need to find the data for, and whatever gets accessed, those 8 data bits will be dumped out on D0 through D7, which travel over to the data bus. And once that data is on the data bus, it travels up and it goes into the microprocessor. Now since each EEPROM is a 4K, these lines, these address lines 0 through 11, could be all zeros to get the first memory location within this particular chip, all the way up through all ones. Now if you think about 12 ones, that would be FFF. Now the next chip is going to be accessed when there's a 1, the not 1 goes low. So to get the not 1 to go low, we would have had to have a high on the A12 line. This line would get that low pulse according to the read, and that would activate this chip. So therefore the A15 through A12 lines have to have 0001 on them, the 1 being the A12, and the A0 through 11 could be anything from all zeros all the way up through, I'm sorry, I'm looking at this chip down here now, could be all zeros up through all ones. So the addresses to access this chip are going to be 1000 up through 1FFF. And the same with the next one is going to be 2000 up through 2FFF. So to determine the scheme, what's helpful often is to draw the 16 bits of memory and label what you know. First of all, the A15 line, remember that's got to be low. So put a low in there, it's always going to be low. The A14, 13, 12 are going to be used, and they're going into the A0 through A2 of the decoder. They're going to be used to pick which one of these outputs gets selected. So you can just say that the A0 is driven from the A12 lines, right? The A12 goes into the A0. The A13 goes into the 1, and so on. So the first hex digit of this 4 hex digit string is used to select the EEPROM. The last 3 hex digits, or the last group of 0 through 12 bits, is going to select which location within the EEPROM. So again, this is used by the 2732 EEPROMs, and they could be all zeros up through all ones, which is 000 hex up through FFF hex. And the first hex digit is going to be either 0000, which is a hex 0, or it could be 0001, which is a hex 1, or 2, or 3 to pick the last EEPROM that we have set up in here. And the other thing to realize is that when you have multiple EEPROMs all connected to the data bus, they all have to be floating except for the one EEPROM that got selected. And that's what this note means, that the D0 through D7 outputs are always floating unless the particular NAS CE is low. So the NAS CE of the one we're choosing is going to go low momentarily, and it's going to allow the D's to travel over to the data bus and up into the microprocessor. So to exercise our knowledge, let's look at example 16.1. Determine which EEPROM and which EEPROM address are accessed when the micro issues a read command for the following hex addresses. So if the microprocessor statement says read 0007, which EEPROM and which location? Well, the solution is right here. The high order hex digit will select the first EEPROM. Address 7 in the first EEPROM will be accessed. Address 7 is actually the 8th position in that EEPROM, right? Because you got to count the 0 position, then 1, 2, 3, up through 7. So it's really the 8th location in that EEPROM. How about read 26C4? Well, 2 is actually going to be the 3rd EEPROM down, 3rd EEPROM, and here I laid out what the A's were going to be, the high order A bits are going to be, and then the address 6C4 in the 3rd EEPROM will be accessed. This next one is 3FFF. That'll be the last location in the 4th EEPROM. And then read 500H is actually an error because there is no EEPROM connected at location at the 5th output of that address decoder. We could have put one there, but in the circuit there is none right there. So back to this diagram, when you look at this, we've got a 4K, 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 4K for a total of 16K. What if we wanted to expand this into a larger system? For example, expansion to 64K. So the memory system back in 1620 can be expanded to 64 by utilizing 2 of these decoders as shown in the next diagram. So the first LS138 is going to select EEPROMs 1 through 8 as long as the A15 is a 0, because this enables looking for a 0. So when A15 is low, that's going to access EEPROMs 1 through 8. When A15 is high, this will be disabled, but look down below, I have that going into the active high enable for the second group. So now when A15 is high, we'll actually be accessing this decoder, and then EEPROM 9 through 16 will be activated based on the inputs to the A0, 1, and 2, which came from address lines 14, 13, and 12. The next application in the textbook is a prom lookup table. In addition to be used strictly for memory, ROMs and PROMs and EPROMs can also be programmed to provide a special purpose function such as a lookup table. A simple example is to use a PROM as a 4-bit binary to gray code converter, as we'll see in the next diagram. First of all, I made a chart of all the binary numbers counting from 0, 1, 2, 3 all the way up through 1111, which is 15, and the corresponding gray code. And the gray code, as you studied back in a previous chapter, goes all zeros and then 1, and then you get 1, 1, and so on. And so the gray code is slightly different. And what if you wanted to use a PROM to convert these binary strings into what their equivalent gray code is? Well, you could program the PROM with all the gray code values and leave the binary input as the addresses that you want to select. And when you select that memory at that address, what's going to be in the contents is going to be the gray code, a 4-bit gray code. So in other words, let's take a look at binary 0101. This would be input into the address lines of this 16 by 4 PROM. 16 by 4 means there's 16 possible locations. Each location has 4 bits at it. So when you enter that number 0101, address 00101 got accessed, and what was there? Well, 0111 was there. So that was the contents, and those contents come out. So basically you're inputting a binary number and coming out with a gray code. This is called a table lookup. Application 16.2 is a digital LCD thermometer. Another application, one that covers several topics from within this text, is a digital Celsius thermometer. In this application, we're going to use a PROM lookup table to simplify the task of converting meaningless digital strings into decimal digits. So we'll look at this diagram now and discuss it. So the heart of this thermometer is this PROM, which is going to be a lookup table, and I'm calling it a 256 by 8 PROM. You'd have to look on the internet to find a PROM or an EPROM that was this exact dimensions. There's 256 locations. At each location there's 8 bits. The 8 bits are going to come out on these cues. Now the A0 through A7 receives its value from the output of an ADC. Now the ADC has got an analog input that's coming off the voltage from a thermistor. So what you'll do is go through experimentation of degrees F. For each degree F, what value of digital string do you get out? And these might be meaningless because the thermistor is nonlinear, but it's repetitive. It'll repeat the exact same result for every degrees F. So you'd build a data table and say, at 1 degrees F I get this digital string, at 2 degrees F I get this digital string, and so on. And then what you would do is make a table that shows these digital strings and use those for an address to point at the EPROM. And then what do you want to see on these displays out here? So at 1 degree C, out here on the last displays is going to be 01. So what you do is put the code 0000 for the high order digit, 0001 for the low order digit, and the BCD to 7 segment decoder would display these 2 right hand segments. So let's pick the number 20 degrees. So at 20 degrees, whatever this binary code is that comes out, we don't know what that is, but you're going to do this through experimentation. You'd build that into the PROM lookup table as an address, and at that address you want to output the number 20 on this display. So to get the number 20, you would input 0010, that's the 2, and then 0000 for the 0. This decoder, BCD to 7 segment, would display this segment, this one, and so on. So you'd see a 2, 0. So basically we've got a PROM lookup to form a digital thermometer. Doesn't get much easier than that. So the last section of the book covers another entirely different type of memory called magnetic and optical memory. So we'll look at that next.